guys, time, wine. Okay, okay, so today our store have a new wine. So we have a great wine here.
Why this one the only one that's different?
Okay, this is our traditional fermented. So, as you know, this is a honey wine, or we call as a mess for our country. So, do you like it?
It looks interesting, but how do you know that it is safe and is a good quality?
That's a good question. I only produce it using traditional methods. To know its quality, scientists need to analyze it.
Why don't you follow us to our laboratory? Our scientists can help you standardize it.
Wow, that's good. Let's go.
Okay.
The next day.
Hello.
Hello, Professor. Hello. So this is the standard that I talked about in our previous call. Now we want to learn more about how analytical chemistry could adapt its traditional method in the making of honey wine. Ooh.
Hello, Professor. I heard a lot about you. Can you show me the process?
I think I can show you the process that involves volumetric analysis for making the wine. And I think that's the easiest method that you can understand. Let's go to my lab.
Alright. You have to watch the video, right? So, have you wondered how scientists determine whether a fermented beverage is safe to drink and a good quality? This is where analytical chemistry plays an important role. So, honey wine, also known as a mess, is traditional alcoholic beverage made from honey, water, and gesho leaf. It has been consumed in Ethiopia for many years during a cultural and religious celebration. However, because it is producing by a traditional fermentation methods, the quality and safety of the beverage can vary from one procedure to another. Okay. To solve this problem, analytical chemistry is used to evaluate important quality parameters such as pH, alcohol content, titratable, acidity, total soluble solids, nutritional composition, and microbial quality. This analysis helps ensure that the beverage is safe, consistent, and suitable for the consumers. Okay, so therefore, the objective of this study to standardize and characterize mass using analytical chemistry. And in this video, we are focusing on the volumetric analysis involved in the standardization.
So, why does acidity is important in wine? First of all, high acidity acts as a natural preservative. It stops bad bacteria and wild yeast from ruining the wine, while letting the good yeast do its job. Second, balance, taste and texture. So, acidity gives wine its crisp, refreshing bite without it taste flat and flabby. It also balances out the sweetness and cuts through heavy alcohol and tannins. Third one, it locks in bright color. If acidity drops too low, the color can shift into an unappealing color and duller color than the yellow.
Okay, for this slide, I would like to talk about the introduction to the analytical chemistry. So firstly, analytical chemistry is an important branch of the chemistry that focuses on the obtaining reliable chemical information to the analytical measurements. It plays a significant role in evaluating the impact of the chemical activities and supporting the environmental protection. In addition, analytical chemistry aims to improve the analytical methods by reducing hazardous substance, minimizing energy consumption, and promoting safer laboratory practice. According to Lopez Lorento ETAL 2022.
So, Gesho is a regional plant used similarly to hops in beer, providing a bitter flavor profile and act as a fermenting agent. So next, honey. Honey is the primary source of fermentable sugars, while water is the liquid base for fermentation medium. Higher honey concentrations provide more substrate for yeast, generally leading to a higher alcohol by volume or a sweeter finish if fermentation finishes before all sugar is consumed. For Gesho control, Gesho is kept at the strict weight to volume ratio relative to the water, showing that even small variations in these ingredients can significantly alter the bitter balance of the brew.
These are the apparatus and materials that we need in order to conduct a titration experiment, which are conical flask, burette, and also the indicator. Before we conduct the experiment, we need to know the basic things about titration first. So, there are two solutions that we will use in this experiment, which are the acid and also the base solution. But how can we know which one will be in the burette and which one will be in the conical flask? The answer is the solution with known concentration will be in the burette, or we call as titrant. Meanwhile, the solution with unknown concentration will be in the conical flask, or we call as analyte. As example, the acid solution is a known concentration, so it will be in the burette. Meanwhile, the base solution with the unknown concentration will be in the conical flask. So the same thing happens when the base is a known concentration and the acid is the unknown concentration. Now, let's see the simulation video of titration experiment. So, as we see in the video, NaOH solution was filled in the burette. That means the NaOH solution is a known concentration. Meanwhile, the HCl is the unknown concentration. The indicator used in this experiment was phenolphthalein, where the function of phenolphthalein is to mark the endpoint of the experiment. How? By analyze changes of color in HCl solution, where the colorless solution will turn to a light pink. Then, that's the endpoint of the titration experiment.
Now that we have covered our lab workflow, let's dive into what these numbers actually mean. When looking at the data, our main goal was to find out which formulation gives the most stable, highest quality product, where the research team have tested 3 variations by adjusting the honey-water ratio and the amount of Gesho added. While formulation 1 and 2 struggle slightly with lower acidity baselines, formulation 3 emerged as the clear winner across every single chemical parameter. So if we look closely at the result of the volumetric analysis, we can see that formulation 3 have the highest titrable acidity, which is 3.50 plus minus 0.00, and the total soluble solids, which is 26.24 plus minus 0.03. Now, let's look into this graph. So, if you look closely at the slight trend curve, we can track that there is something fascinating like a chemical transformation happening. So, the pH of the formulation 3 have been decreased steadily from 4.23 to a 3.82 from day 1 to day 21. So, why does this drop happen? This drop happened due to the lactic acid bacteria, which convert the honey sugars into organic acids. However, a simple pH reading doesn't mean anything. It could not prove something. Hence, that's why the volumetric analysis comes. So, by using the method before and looking at the result, the volumetric analysis have also proven that formulation 3 has the highest titratable acidity, which is 3.50 grams per liter. And also, it also have a highest soluble solid, which is 26.24. The high concentration of organic acid in the formulation 3 acts as a natural preservative, protecting the beverage from spoilage pathogens while preventing a flat, unappealing taste.
In conclusion, analytical chemistry successfully resolved the quality and safety inconsistency of traditional fermentation. How? This is by successfully achieving a scientific blueprint for standardized mass production. Out of 3 tested ingredient variations, formulation 3 was selected as the highest quality version.